Light is one of the fundamental components of our universe. It can be considered as the language that humans use to communicate with the universe. In this lesson, we will cover all the basics of light, starting with how does light take part in physics. Physics is the study of nature and all of its components. Components like matter, which includes all the atoms and particles, which makes up everything that you can see in the universe, such as the solar system and the planets and everything, including you and me and everyone else. Another component of our universe are the fields. Fields are regions that exert external forces. For example, the gravitational field, which pulls everything towards the Earth. You also have the magnetic field, which attracts magnetic materials. And of course, the electric field, which is the field that causes the attraction between charges. Another major component is of course light. Light comes from matter. The type of matter that gives out light are called as luminous objects. They emit light, which means they radiate it and spread it out from the source in the form of straight light rays. Luckily, when light enters our eyes, we can see things. Light is made up from fields, specifically the electric and the magnetic field. Light also interacts with matter. It comes from matter, and matter can interact with light in several ways. Objects that do not emit light are called as non-luminous objects, and those are some examples of those objects. And that's the part that light takes in physics. Now let's look at light and matter interactions. To do that, look at the following setting. The lamp on the ceiling is considered as a luminous object. Why? Well, because it's an emitter. It emits light. It emits it as light rays in all directions, millions and millions of those light rays. And those light rays are able to travel through air. And this makes air a non-luminous object. Why is it non-luminous? Well, because it does not emit light. However, it transmits light. So this type of non-luminous object is a transmitter, which means it allows light to pass through it. Other examples of transmitters include glass and water. If we extend those light rays towards the mirror on the side, we will notice that those light rays will bounce off the mirror. So the mirror is a non-luminous object because it does not emit light. However, it still interacts with light, and this time it reflects the light. The mirror is a reflector, and we call this type of reflection as regular. To understand the meaning of that, I want you to look at the light rays going to the TV cabinet. They will also be reflected, but in random directions, unlike the reflection of the mirror. So this is called as diffuse reflection, where you can't see an image from a diffuse reflector. You can see your image in a mirror, but you can't see your image if you look at a piece of paper, for example. So to get a clear picture, look at this diagram. In regular reflection, light hits the mirror and then reflects in the same pattern, but in diffuse reflection, because the surface is not as smooth as a mirror, light bounces in random directions. Therefore, no image is formed. Diffuse reflection happens from most material. For example, if we take this light ray heading towards the cake, well, the cake is going to reflect purple light towards the eyes of the pet. Similarly, if we take a light ray towards the sofa, then red will be reflected. Of course, there are millions of light rays hitting and they reflect in all directions. They diffuse, reflect in all directions. That's why everyone in the room can see everything. But for this example, we chose the one that is reflected to the eyes of the pet, and that's how it can see the sofa. If we also extend the light ray coming from the TV cabinet, it will also reach the eyes of the pet, and that's how it can see everything. Now, if we extend one light ray towards the TV, well, the TV is going to absorb this light ray. It's a black surface, and black surfaces are usually absorbers. They do not reflect light, they do not allow it to pass through, they just consume it inside them. So this is the third type of non-luminous objects, which is an absorber. In general, those are the light and matter interactions. We have luminous objects, they emit their own light, and we have non-luminous objects. They do not emit light, but they still interact with light in several ways. We have reflection in its two types, regular and diffuse. The main difference happens because of the smoothness of the surface. If the surface is smooth, regular reflection would occur. And then you have absorption, which happens from black or dark surfaces, and you have transmission, which happens from transparent materials, materials that allow light to pass through. And that's the end of light and matter interactions. Now let's go to the light nature itself. What is light made up from? If we take a laser, and a laser is just a device that emits monochromatic light, which means light of single color. So let's say it emits red light, and light is actually the fastest thing there is in our universe. It travels with a speed of 300 million meters per second in vacuum, and yes, it can travel through vacuum, although it's actually made up from a wave. And as we studied before, waves need a medium, but light is a special type of wave. So what does that mean, made up from a wave? Let's zoom in into it. If we look at it, well, similar to water waves, we know in water waves you have ripples of water particles. The water particles go up and down in a transverse manner. Light also has electrical field going up and down in a transverse manner, similar to water waves. But that's not the only thing. Light also has a magnetic field going left and right. So light is actually made up not from one, but two transverse waves acting in this weird way that is unintuitive to us because we cannot see something like that traveling in nature. And the thing about those two changing fields is that the angle between them is 90 degrees. So that's it. Light is basically changing electric and magnetic fields. They move in a wave pattern, transverse wave, similar to water waves, and the angle between those two separate waves is 90 degrees. And since it's made up from electric and magnetic fields, this is where the scientific name of light comes from, which is called as an electromagnetic wave, in shortcut EMW. Keep this in mind. So that's what light is made up from. Nothing special, but that's how it is in our universe. Now going to the second section, which is the relation between the light wavelength and colors. Since light is a wave, well, every wave has a wavelength, frequency, and so on, all the wave properties. Let's take two lasers. One emits red light, the other one emits violet light. If we zoom in into them, we know it's made up from waves, and for simplicity, this is how I'm going to represent the waves, just one of the transverse waves, no need to draw both of them. So for red, if we measure the wavelength, which is the distance from peak to peak, we'll find it to be extremely small, of 700 nanometers. If we do the same for violet, we will even find it much smaller than that with just 400 nanometers. And that's it. Basically, the main difference between colors is just the wavelength. Red has a larger wavelength than violet. They are still made up from an electric and a magnetic field. Same everything, the only difference is just the wavelength. And this is the visible light spectrum that humans can see. Humans are able to see from 400 nanometers to 700 nanometers. As each wavelength, when it enters our eyes, our brains gives us the illusion of a different color. For example, 550 would appear green, 600 yellow, and all the colors you can see in this diagram. To get a clear picture, let's look at this TV, switch it on, and then you see this image. To the observer, well, from the orange surface, orange color hits the eye and then enters the screen at the back of the eye in this pattern. Light green also does the same from the other side, and basically all the colors from the screen are emitted towards the eye, and an image is formed in this pattern on the back surface of the eye, the fovea. The brain then translates this into an image. Alright, now I want you to notice one thing. From those spectrum from 400 to 700, those are the colors humans can see, you notice that you don't have white nor black colors, because those are a bit different. To understand them, I want you to look at the following item. You have a piece of paper, and all of the 7 rainbow colors were drawn into it. Red, orange, yellow, green, indigo, blue, and violet. Now this piece of paper is attached below to a motor. When you switch on the motor, it's going to rotate so fast. So watch carefully. As you notice, when it's rotating, the colors are being mixed together so fast that you get the illusion of white color. And this is what white color is. It's basically when all the colors come at once. Or not even all the colors, just the 3 primary colors, green, red, and blue. If you mix the three primary colors together, when they hit the same spot in our eyes, our brain will understand this, will give us the illusion of the color white. So for example, from the white portion of the parrot, all the three primary colors or all the colors are being emitted to the same spot in the eye. And when this happens, our brain mixes all of them together and they appear white in color. So this is how white is. There is no single wavelength of white light. White is when either the three primary colors or all the colors enter at once and hit the same spot in our eyes, then our brain will mix them all together and form white. So that's about white. Now let's see, what does black mean? And to understand this, I want you to imagine switching off the lights. What do you see? Well, yes, exactly, you guessed it. You see black. Basically, black is the absence of light. So to understand this more, look at the following setting. From the light source, which emits all the colors, therefore they appear white. As they go to the white side of the t-shirt, while the white side of the t-shirt will reflect all the light in all directions, and one of those reflections will reach the eye. Since all of the colors are hitting the eye at the same spot, then they would merge together and appear white. Similarly, when another white ray hits the red portion of the t-shirt, well, this part is going to reflect red while absorbing all the rest. So it will reflect the red part and absorb the yellow, the green, the blue and the violet, all of them. And that's how it appears red in our eyes. Similarly, if it goes to the blue portion, well, the blue wavelength is going to be reflected to our eyes. That's why it appears blue, while the rest will be absorbed. However, if it goes to the black hat, nothing is going to be reflected. All of the wavelengths from 400 to 700 were absorbed, and therefore nothing reaches your eyes. That's why that part appears black, similar to when you switch off the lights in your room. So keep this in mind. Surfaces of materials, they can reflect all the light, therefore appear white. They can reflect none of the light, therefore appear black. Or they can reflect parts of the light. If they reflect blue, they will appear blue. If they reflect green, they will appear green, and so on. And that's it. That's the relation between wavelength and colors. Next in our list is the invisible light. If you look at a rainbow, you will see light in its spectrum from violet to red, and this basically happens because of the raindrops that stay in the sky even after the rain finishes. Those raindrops, they take the white light coming from the sun and separate it into its components from red to violet. Newton tried to replicate similar effect in the labs, and he wanted something to separate the white light into its components similar to what's happening in the sky. So he used a triangular prism. Now this triangular prism acts the same as a raindrop. When white light comes in, it's going to disperse it or separate it into its main colors from 400 to 700 nanometers. And that's how Newton proved that white is basically made up from all colors or wavelengths by observing rainbows in nature and replicating the same in a lab. Another scientist, Herschel, devised another experiment, and he wanted to measure the temperature of the light. So what he did, he placed thermometers at different lights. He placed one in the violet region, one in the green region, and one in the red region. And he noticed that the temperature increases when light hits the thermometers compared to the environment. However, he noticed that as you go towards the red, the temperature increases more than in violet. And then he thought he will place the thermometer just a bit above red in this position. Shockingly, he discovered that that was actually the highest temperature, even higher than red. And this initiated the idea that there might be light that humans cannot see. We can see from 400 to 700 nanometers. 400 is violet, 700 is red. So this means there is a portion that is still above 700, and that portion is not visible to humans, but it can heat objects even more than the light that we can see. From this discovery, another question arises, which is there light that has a wavelength below 400 nanometers? And it turns out there is. If we analyze the light coming from the sun, we would notice, of course, the visible portion of it, which is between 400 nanometers to 700 nanometers and about the same size as microorganisms, and luckily it's visible to us. There is also a part that is beyond 700 nanometers, and we call that type of light as infrared, in shortcut IR. And the thing about infrared, although we cannot see it, we can sense it, because when infrared hits materials, they absorb it and they heat up, such as our skin. Infrared extends to about the same as the thickness of a drawing pin. Similarly, later experiments showed that ultraviolet light also occurs, which is the light that has a wavelength less than violet, up to 10 nanometers, about the size of molecule. But that's not the full story. There are also microwaves, which extend from 1 millimeter to about 30 centimeters in wavelength. And there is even more than that. You have radio waves. And radio waves extend from 30 centimeters and they could reach a whopping wavelength of about 100 kilometers even in space, or let's say the height of buildings on Earth. You also have X-rays, which have a wavelength that is even less than 10 nanometers of violet. Extremely small, they could reach 0.1 nanometers, about the size of atoms. And that's not the full story. We still have gamma rays, which are even smaller than that, could reach a wavelength of 0.01 nanometers, the size of an atomic nucleus. So in general, those are the 7 types of light. You have gamma rays, X-rays, UV, visible light, the light that we can see, which turns out to be a very small portion of the light. And then you have infrared, microwaves, and radio waves. As you go from gamma rays to radio waves, the wavelength increases. And if you remember, the wave equation says that the speed of a wave equals the frequency times the wavelength. In this case, for the speed of the wave, we'll use capital C, which represents the speed of light. Since light has a constant speed in vacuum of 3 times 10 to the power of 8 meters per second, we can rearrange this formula and make frequency as the subject, which equals the speed of light divided by the wavelength. And from this formula, you notice as the wavelength increase, and since the value C is constant, then the frequency, the number of waves every second, is going to decrease. So as you go from gamma rays to radio waves, the frequency decreases. And the thing about light is that when it has more frequency, it has more energy. So as you go from gamma to radio waves, the frequency decreases. Therefore, the energy of the light must decrease. Energy is linked to frequency. Think about frequency is how many fluctuations happen every second. So definitely if you have more fluctuations happening every second, then it must have more energy. And that's it. Those are the invisible lights that exist in our nature. What is special about the visible light that we can see? Nothing really. It's the same as the rest. It has wavelength and all the properties. The only special part about it is that when it enters our eyes can detect it. It's like our eyes are measuring devices. Now let's look at some of the applications of the invisible light. Starting with radio waves. Stars are natural emitters of radio waves, but it can also be made artificially in labs. For example, if you have a person talking into a microphone, the microphone will convert the sound energy into electrical energy. And if we connect this electricity to an antenna is a device which will convert those electrical signals coming from the microphone, which represent sound, into radio waves transmitted in all directions. So if you have a radio device in the way and it detects those radio waves, well then another person can hear the original sound that is generated. This is one of the major uses of radio waves. It is used in radio broadcasting. Another thing you need to note about radio waves, which is since it has large wavelength, as the waves hit boundaries, for example such as this mountain, well after they leave they are going to diffract and spread more. That's one of the benefits of radio waves. It has a high reach. This is similar to the water diffraction we studied earlier. Next is microwaves. Some consider microwaves as actually parts of radio waves, but that's fine. Let's look at the uses. Microwaves are used in mobile transmissions and Wi-Fi. They're also used in satellite TV reception and transmission, and of course, microwave ovens. So let's see how microwave ovens work. If you place a slice of pizza inside, well, we know food contains water particles. It contains amount of moisture. When microwaves are generated, the thing about those water molecules, they will absorb those microwaves, which will cause them to vibrate more. And more vibrations means it's being heated. That's the idea of a microwave oven. Now let's look at infrareds. Basically, infrareds are emitted and absorbed by most objects. They cause heating effect. To understand that, I want you to look at the following light spectrum. Let's say we have a hot cup of coffee. Usually this cup of coffee will emit infrareds in this region. Of course, we cannot see those emissions because they are infrareds. But if we take an object at a higher temperature, such as the charcoal, you can see it starts to glow red. And that's basically because charcoal emits infrareds, and it even emits more energetic type of light, which is red. We can feel infrared as heat, and we can see red as light, as color. If we take a hotter object, for example, this heated glass over here, you can see it even starts to emit orange and yellow, plus infrared, of course. So the thing is, the more you heat objects, the more type of radiation they emit, not just infrared. So if we have a hotter object, for example, our sun, then you will get infrareds and all the visible light plus some UV. That's why the light coming from the sun appears as white, because you are basically emitting all the spectrum of the visible light. Some animals have the ability to see infrared. For example, snakes. That's how they can detect their prey at nighttime. Humans also develop devices that converts infrareds to reds. For example, a thermal camera, which can detect infrared and then change it to red so that we can see it. Now let's look at ultraviolet, or in shortcut, UV. Well, the sun is a natural emitter of UV. The UV with high frequency, which means a very low wavelength, can be harmful. It has the ability to penetrate the skin and can cause skin cancer. To protect ourselves, we need to use a sunscreen during sunny occasions so that the UV will be reflected. Different skin colors have different protection against UV. Darker skin has a natural protection against UV. That's why a dark-skinned person is less likely to get skin cancer. Also, some materials, or animals even, can glow when they are subjected to UV light. Such as scorpions, they contain a lot of proteins that they glow when UV is illuminated at them. Usually people in the deserts, they take a UV lamp with them to detect those insects in their area. Same as blood stains, for example. Blood contains proteins, and those certain proteins, they can absorb UV and glow. Materials that glow with UV are used in identifying real money notes, as you can see in the top picture, and UV lamps are also used to attract insects, as insects has the ability to view UV and they assume this is proteins, a source of food. They are attracted towards it until they reach the trap and they get electrocuted. It is also used in a lot more applications, such as sterilizing. It has the ability to kill bacteria and viruses, and also in tanning beds. Now let's look at X-rays. They are even more harmful than UV to humans. They have the ability to penetrate flesh, but not the bones. That's why they are used in medicine to produce images. X-rays are illuminated to the parts where you have broken bones, and then you kind of look at the shadow of this light, the shadow of the bones actually, because it can penetrate the flesh. Now, although X-rays are harmful, but they are only used when necessary for short intervals of time. You don't take selfies using X-rays, you just do it maybe once or twice in a lifetime, when it's needed and recommended by a doctor. They're also used in security systems, for example, to check luggage in airports, and also several medical and engineering applications. Last thing is gamma rays. And gamma rays are the most dangerous type of electromagnetic waves. They have high penetrating ability because of its extremely small wavelength, and they do come from radioactive elements, which will be discussed in the chapter of radioactivity later. They are used in medicine to produce images similar to X-ray images, but different mechanism. This time the person drinks a fluid that contains radioactive materials that emits gamma rays before you do the screening. and then the person lays down on the machine while their body emits gamma radiations. The machine detects all these radiations and form an internal image of the body. Gamma rays are also used in cancer treatments, as concentrated gamma rays are directed towards the tumors. Now the thing about gamma rays, they are dangerous in a way that they have the possibility to change the DNA. And that's basically the idea of the Hulk move. It is assumed that this person has a changed DNA due to gamma rays. But in reality, when gamma rays change the DNA, they could cause cancer. Yes, they are used to treat cancer, but that's only if you already have cancer. And those are some of the applications that you need to keep in mind, and not all of them actually. The last thing in this lesson is to look at the relation between light and energy. To emit light, energy is needed. Luminous objects, they convert from one form of energy to another. For example, the sun converts from nuclear energy to light energy. A fire converts from chemical energy to light energy. A bulb or a laptop, any screen basically converts from electrical energy to light energy. You need energy to generate light. And when non-luminous objects absorb light, they do gain energy. For example, a black surface or even a colored surface. When white light hits them, a black surface will absorb all of it, while the blue surface over here will reflect light, still absorbing the rest. In this case, the materials will heat up and light energy is converted to thermal energy. Also, leaves, when they absorb light, they convert it into chemical energy stored in the fruits of the plants. And a solar PV cell, when it absorbs light, it converts it into electrical energy. So to emit light, you need energy. When you absorb light, you gain energy. And that's the end of today's lesson. I hope you enjoyed it. Thank you so much for being patient. Don't forget to like, subscribe, and share. And stay tuned for the coming lessons.